So we have seen that we can formulate a very good approximation of the error performance, and the approximation somehow is a little bit vague. And now we're going to derive a rigorous bound on the error probability using stopping sets. So how can we rigorously bound the approximation? And for this, we first introduce a result from probability that is very, very useful. And that's the following one. So it's called the second moment method. So we have a discrete random variable x that is non-negative. So x takes on values larger or equal than 0. And then we calculate the probability that x is strictly larger than 0. This is 1 minus the probability that x is equal to 0. And this is something that we can upper bound, or we can lower bound in the following way. So we can lower bound this guy as the expectation of x squared divided by the expectation x squared. And essentially, this is just Cauchy-Schwarz inequality in disguise. So Cauchy-Schwarz inequality, when we apply to random variables, says that the expectation of x times y squared is smaller or equal than expectation of x squared times the expectation of y squared. And now we can just formulate the expectation of x. So the expectation of x is the expectation of x times the indicator variable that x is larger than 0. Because when x is equal to 0, this term will have no effect on the expectation. So we can just look at the expectation of x being larger than 0. So it's the expectation of x times 1, the indicator function of that x is larger than 0. Then we apply Cauchy-Schwarz. This is Cauchy-Schwarz of expectation of x squared times the expectation of the indicator variable that x is larger or equal than 0 squared. An indicator variable can take on values 0 or 1. So we square 0, we get 0. We square 1, we get 1. So we can remove the square, doesn't change anything. And the expectation of an indicator variable is just the probability that this random variable is larger than, or that the condition is fulfilled. So it's just summing up certain probabilities, and in this case it's the probability that x is strictly larger than 0. And then just rearranging the terms, get this expression. We're going to use this expression to prove a rigorous lower bound on the error probability. So the way we do this is we indicate, or we insert a new variable. So we insert N2SS, and that's the number of stopping sets in the graph that are erased. Number of size 2 stopping sets in the graph that are erased. So, and 2SS is then the following. And 2SS is the sum from I going from 1 to n, and j going from I plus 1 to n of Vij. And we denote this as the sum from 1 ij between 1 and n. So we look at all the combinations of I and j, and the order doesn't matter. That's why we can do this summation. So Vij is the same as Vji. So we only need to look at one of those two cases. And Vij is the indicator variable that both Vi and Vj form a stopping set, and they are also erased. In contrast to U was just forming a stopping set. Now we also want them to be erased. So that's why we call it V. And essentially, N2SS is just a random variable. The sum of random variables Vij, so it's a random variable. So let's take a look at how we can proceed from here. So first what we do is we calculate the expectation of the random variable N2SS. It's going to be clear later why we are going to do this. So the expectation of N2SS is just the expectation over the sum over all ij of Vij. Now we can use the linearity of the expectation. So the expectation of a sum is the sum of the individual expectations. So it's the expectation, the sum over all combination of ij, the expectation of Vij. The expectation of Vij is 0 times the probability that Vij is equal to 0. Sorry for the mistake here. This should be a 0. Plus 1 times the probability that Vij is equal to 1. And this is just the sum over all combinations of ij of p, Vij is equal to 1. And because Vij does not depend on a very specific I and j, it's the same for every I and every j by construction, by the channel. This is just n choose 2 because that's the number of possibilities of the probability that Vij is equal to 1. So we have the expectation. So now we can say that this expectation of N2SS is the probability that Vij is equal to 1. And that's the probability that Uij is equal to 1, Vi is erased, and Vj is erased. Because of independence, this is all of these three variables, they are independent. This is the probability that Uij is equal to 1 times the probability that Vi is erased times the probability that Vj is erased. And that's the expression that we had before. So that's epsilon squared times n choose 2 times the probability that Uij is equal to 1. So now we can bound actually. So the probability PE, the error probability of an erroneous code word, is the probability that at least one stopping set is erased. And this can be every possible stopping set. So this is larger or equal than the probability that N2SS is larger or equal than 1. So we just focus on stopping sets of size 2. And obviously this probability is smaller because we neglect all the other possible stopping sets. So we need to look at, we neglect essentially all the other stopping sets. And this is why we get something that is smaller. So now we apply the second moment method. Second moment method is applied here. And we get that this is equal to the expectation of N2SS, which we have just calculated, squared, divided by the expectation of N2SS squared. So this is something we have. This is written here. Now we need to calculate this guy. This is going to be a little bit more complicated, unfortunately. So it's not going to be too easy. And we're going to spend considerable amount of time calculating that one. We're going to calculate N2SS squared now. So let's get to it. We calculate the expectation of N, what's the notation? N2SS squared. And now we just insert the definition of N2SS. It's the sum over all ij, Vij squared. Therefore, from this we take the expectation. So and this is equal to the expectation. Now we just factor out this squared term. So first we have the squared terms. So it's the sum over all ij of Vij squared plus the sum over all ij, the sum over all kl, and ij is different from kl, of Vij times vkl. Okay, so this is equal to the expectation or now we just apply the linearity of the expectation again. So it's the sum over all ij, expectation of Vij squared, plus sum over all ij times sum over all kl. Ij must be different from kl of Vij times vkl. Again, Vij is an indicator variable, it's 0 or 1, so Vij squared is equal to Vij. So this is the expectation of Vij. So this is equal, this is something that we have already calculated. This is epsilon squared times n choose 2 times the probability of Uij is equal to 1 plus this remaining terms, sum ij, sum of all possibilities of kl. Ij is different from kl times, and here I was a little bit sloppy. I missed writing down the expectation. Times the expectation of Vij times vkl. So this is something that we know. Now we need to calculate the expectation of Vij times vkl. So now we calculate the expectation of Vij times vkl. So that's going to be tough, just as a warning, and we're going to speed up the process in some cases, just because it's very similar to what we did before. So the derivation is very similar to the counting argument that we did before, and now we're just going to look at it from a slightly different point of view. So we have essentially two cases. So we look at the first case. So look at case number 1. So Vi and Vj form a size 2 stopping set. So I is different from j. And now Vk and Vl form another size 2 stopping set, where now, without loss of generality, we assume that they share a variable node. So they share one variable node, and that's k is equal to j. So we say that k is equal to j, which means both stopping sets share a variable node. So that means that the expectation of Vij times vkl means that we can replace k by j. And that's nothing else as the probability that Vij is equal to 1 and Vjl is equal to 1. Because that's the definition of the expectation. So we look at Vij vkl times the probability that the different outcomes happen. And Vij and vkl must both be equal to 1 in order for the expectation to happen. So now we just do some manipulations. So we calculate the probability that Vjl is equal to 1, even that Vij is equal to 1, times the probability that Vij is equal to 1. This is just a base theorem applied. The probability that Vij is equal to 1 is equal to epsilon squared times the probability that Uij is equal to 1. Then we have multiply this with the probability that VJL is equal to 1, given that Vij is equal to 1. This is equal to epsilon squared times the probability that Uij is equal to 1 times the probability that UJL is equal to 1. Vj is erased. I'm going to use some shorthand notation here. VL is erased. Given that Uij is equal to 1, and given that Vi is erased, and given that Vj is erased. So this is equal to epsilon squared times the probability that Uij is equal to 1 times epsilon times the probability that UJL is equal to 1, given that Uij is equal to 1. Because Vj is erased is already given, so this has no effect on this Vj. We know that Vj is erased. The probability that Vj is erased is going to be 1, because we know it already. So it's just the probability that VL is erased, so we have a single epsilon. So now we need to calculate this probability, UJL, given that Uij is equal to 1. So this is everything this we know already. So we're reducing it step by step onto something that we don't know, and then we calculate this one. And for this, we use a very similar argument as before. So we're going to look at case. We have check nodes. We have 3 check nodes, each with DC sockets. And I'm going to use the example that we had before. So we have node Vi, a variable node Vj, and we have variable node Vl. So we assume that Vi connects to the first socket of the check nodes. We assume that Vj connects to the second socket. So Vj occupies the second socket, and now we need to get VL. So in order for VL to form a stopping set with Vj, it must connect to the same check nodes as Vj. So the only possibility is that it connects to one of those empty sockets. For instance, this could be a situation. So that's the only possibility. And essentially, the argument is exactly the same as in the previous lemma that we calculated in the previous video. So we used a very similar argument as before. And we calculate that the probability that UJL is equal to 1, given that Uij is equal to 1, is equal to dv factorial times dc minus 2. That's the difference, because now we already have 2 sockets that are occupied. So we can only choose from dc minus 2 remaining sockets. That's why we have a dc minus 2. Divided by dv factorial, sum from L from 0 to dv. dv choose L, m minus dv choose dv minus L. Then we have dc minus 2 to the power L times dc power dv minus L. Again, we multiply numerator with 1 over dc power dv, and denominator 1 over dc power L and 1 over dc power dv minus L. So we get a term. So it's 1 minus 2 over dc divided by dv. This will also cancel, divided by the sum from L going to 0 to dv. dv choose L, m minus dv choose dv minus L, dc minus 2 power L times, this is then, we have 1 minus 2 over dc to the power. So now if we look at this, so what we are calculating is this guy. So we need to calculate this guy, or we need to calculate an upper bound of this guy. Because if we have an upper bound of this guy, we can continue the inequality over here. So we can further lower bound this. So for instance, if e to the power n2ss squared is smaller or equal than some upper bound, I call it b bar, that means that this guy is larger or equal than the expectation of n2ss squared divided by b bar. So we can find an upper bound on expectation of n2ss, and this will allow us to continue the argument of the inequality over here. So this is why we upper bound this term, because we want to get something simple, to get a simple expression. So n2ss is essentially, we have this guy here. So we just upper bound this guy, which means we upper bound this probability. So we upper bound P ujl equals 1 given uij equals 1 using the dominant term in the denominator. So if we lower bound this guy, it means we upper bound this guy. So we just use some of those terms that will give us an upper bound of the overall expression. So when we do this, we get the following. So we get P u j l being equal to 1, given u j ui j equals to 1, is upper bounded by just the dominant terms. The dominant term is the one for L equals 0 in this case. So we have the sum over L equals 0 plus sum over L equals 1. And we know that 1 over A plus B is smaller or equal than 1 over A. So we just use the dominant term for L equals 0. So this is then equal to 1 minus 2 over dc to the power dv divided by m minus dv choose dv. So and now we also have this guy for dc larger than 2, and dc is always larger than 2. So for dc larger than 2, this term is between 0 and 1. And this term to the power dv will be between 0 and 1. So this term is smaller or equal than 1 divided by m minus dv choose dv. Very crude approximation, very crude bound, but we are interested in a bound. So this is 1 over m minus dv choose dv. Okay, so now we can take a look at the general case. So that was the first case. Now we look at the general case where the two stopping sets don't share a common variable node. So let's take a look at the general case. In the general case, we have the following. I is an element from 1 to n. J is an element from 1 to n except I. K is an element from 1 to n except I and j. And L is an element from 1 n except I, j, and k. So we have Vi and Vj form a stopping set. So it means they share dv check nodes. And now we assume that Vk connects to B of these shared check nodes. So again, let's draw an example. So again, we use the example for dv equals 3. So we just draw the situation first. We draw a couple of check nodes with the sockets and another one here. So we have check node, variable node Vi, variable node Vj, variable node Vk, and variable node Vl. So Vi connects to the first socket of the first dv-1 check nodes. Vj connects to the second socket of the shared check node. So they form a size 2 stopping set. And now Vk connects to B of those two check nodes. We have B connection to those two check nodes. So here B is equal to 2. And we have 1 connection to another check node. That's one of the remaining check nodes. So and now for VL to form a stopping set, it must connect to the same check nodes as Vk. So it must connect this check node and this check node. And it must connect to this check node. So here, that means we have dv minus b connections here. So now we can calculate the expectation of Vij times Vkl in the following way. So it's the probability that Vij is equal to 1 times Now we marginalize over B, the sum from B going from 0 to dV, probability that VKL is equal to 1. We have B shared check nodes, and given that Vij is a stopping set, so Vij is equal to 1. And we call this probability, we call it PCB. That's the one that we're going to bound now. So again, we're looking for an upper bound of PCB. Similar to what we did here. This is very similar. So we're looking for an upper bound of PCB. So what is PCB? So let's calculate PCB. So PCB, black color, PCB is equal to probability that VKL is equal to 1, B shared check nodes, and Vij is equal to 1. And this is equal to epsilon squared, the probability that K and L, I'm just leaving out a few steps here, the argument is the same as before, the probability that K and L variables Vk and Vl are erased, times the probability that U KL is equal to 1. We have B shared check nodes, given that Uij is equal to 1. This is equal to epsilon squared times TSSB divided by T tilde. Because again, we have a Laplace experiment. So TSSB is the number of possibilities of forming a stopping set with B shared check nodes and the situation given in this picture. And T tilde is the number of all possible connections. So first, again, we start with TSSB. We count TSSB, and TSSB is what we call TIJKB times TIJK L and B. What's this? So the first part is the number of ways to connect Vk. The second term is the number of ways to connect Vl such that UKL is equal to 1. Okay, we start with the first one. The first one is easy. So just counting the number of ways to calculate Vk. And let me just copy this term so that we have a visual aid. Copy and put it over here. Okay, so we count this T E I J K B. So first, again, we have dv factorial possible permutations of the edges. That's easy. Then we need to choose B out of the edges. dv choose B. I'm simplifying the argument, but the argument is just works in the same way as we did in the previous lemma. So, simplifying, but the argument is exactly the same. So it's dv choose B edges that we connect to the already connected check nodes. Then the remaining ones are from M minus dv remaining check nodes. We need to select dv minus b edges. Then the b edges, they can connect to dc minus 2 sockets. That's dc minus 2 to the power b times dc. The other ones can connect any of the dc3 sockets. That's dc to the power dv minus b. Okay, that's the first guy. That's the easy one. Now, the second one is going to be a little bit more complicated. And again, let me put the picture over here so that we can see what we are working with. Put it on top here. It's now we need to do a little bit more effort. So T, I, J, K, L, and B. So now we're counting the possibilities of connecting VL. Again, we have permutation on dv, so it's dv factorial. And now the first B edges, they can connect to dc minus 3 sockets. So you have dc minus 3 to the power b times dc minus 1 to the power dv minus b. Okay, so now we put everything together, and then we can get here as b. So that's dv factorial squared. That's essentially this term times this term. This term times this term. So we multiply the two terms. So it's, let me just write it. And it's dv factorial squared times dv choose b. It's m minus dv choose dv minus b. Very similar argument as before again. Times dc times dc minus 1 to the power dv minus b times dc minus 2 times dc minus 3 to the power b. Okay, now we simplify, or we start simplifying this. So we rewrite it a little bit. So we put everything that depends on b together. So it's dv factorial squared dv choose b times m minus dv choose dv minus b times dc times dc minus 1 to the power dv times dc minus 2 times dc minus 3 divided by dc and dc minus 1 to the power b. So now we simplify this because we take this guy and say this guy is smaller or equal than dc minus 2 divided by dc. Because dc is a positive number. So for positive numbers, we have x minus 1, or for a and b positive, we have a minus 1 divided by b minus 1 is smaller or equal than a divided by b. So 3 over 4 is 2 over 3 is smaller or equal than 3 over 4. As an example. So a, b larger than 1 actually. So we bound this in this way, so we get an upper bound. Look at this line, so I have not enough space. This is smaller or equal than dv squared times dv choose b, m minus dv divided by dv minus b times dc times dc minus 1 to the power dv times, this is 1 minus 2 over dc to the power 2b. Because we square, now we have dc divided dc minus 2 divided by dc, and we have it 2 times, so we square it, so that's why we get 2b, power 2b. So now we need to calculate t tilde. It's going to be very, very tough, but luckily we don't need to calculate it, but we just bound it. So we need a lower bound on t tilde because we want to have an upper bound on PCB. That's a little bit of tricks. Where do we need to lower bound? Where do we need to upper bound? This is something that you need to think about a little bit, or write it down, the chain of inequalities, so that it gets clear. So we do not calculate t tilde, but bound it using a simpler term. The simpler term is when we have no common check nodes. So that means that t tilde is larger or equal, so we just count the cases with no common check nodes. So again, we assume that one of the variable nodes is already filled, and then we just need to calculate the connections of the other one. So that's dv factorial squared times m minus dv choose dv. So that's the first. The first guy can choose from m minus dv empty non-occupied check nodes and then connect to those. The second guy can choose from m minus 2 dv from check nodes and connect to those. And then each of those has dc empty sockets, so it's dc to the power 2 dv. Okay, so now we have everything together to bound PCB, and let's do this. So we know that PCB is equal to epsilon squared times TSSB divided by T tilde. This is smaller or equal than epsilon squared. We insert our bounds. So the first one is dv choose b divided by m minus dv choose dv minus b times dc minus 1 power dv times 1 minus 2 divided by dc to the power 2b. That was our bound on TSSB. And now we insert the bound on T tilde. So that's m minus dv choose dv, m minus 2 dv choose dv times dc to the power 2 dv. So and now we want to get rid of some terms. So here we multiply with 1 over dc to the power 2 dv. And so we get rid of this term. And we do the same in the numerator. So 1 over dc to the power 2 dv. So let's do this. So this is equal to epsilon squared times, start in the numerator, and we put all the combinatorial terms, the binomial coefficients together. So dv choose b times m minus dv choose dv minus b divided by m minus dv choose dv divided by m minus 2 dv choose dv. And then we multiply this with we have 1 minus 1 over dc to the power dv. And we have 1 minus 2 over dc to the power 2b. Okay, so now what we do next is we bound the factorial. So we bound the factorial in the following way. Let's do a side calculation. So would like to bound m minus dv, choose dv minus b, divided by m minus dv, choose dv. So let's write down what we have. So this is m minus dv factorial divided by dv minus b factorial divided by m minus 2 dv plus b factorial. And then we look at the denominator. So we have m minus dv factorial. And in the numerator, we need to put then dv factorial times m minus 2 dv factorial. So this guy cancels already. And now we're going to write down what we have. So if we write out all these factorials, so we can put together this guy and this guy. So then we will have this dv times dv minus 1 up to dv minus b plus 1. And then we put together this guy and this guy. And that's going to be m minus 2 dv plus b up to m minus 2 dv. Okay, so now we bound this, and we bound this rather crudely. So the numerator is smaller or equal than dv to the power b. And the denominator is larger or equal than m minus 2 dv to the power b. So we need upper bound the numerator, and we just take the largest term, and we assume that this is smaller or equal. This is smaller or equal than dv. This is smaller or equal than dv, and then we have dv to the power b. And in the denominator, this is larger or equal than m minus 2 dv. Every term is larger or equal than m minus 2 dv, and so on. And then we bound this by m minus 2 dv to the power b. Okay, so we can take this. We have epsilon squared times dv choose b divided by m minus dv choose dv times, we put our bound. So this is not being equal anymore, but this is upper bounded as dv power b divided by m minus 2 dv to the power b times 1 minus 1 over dc to the power dv times 1 minus 2 over dc to the power 2b. So now what is this guy here? Can we further simplify this guy over here? We're going to rewrite it a little bit. So this guy over here is equal to dv power b. And now we just insert the definition of m. So this is n times dv over dc minus 2 dv to the power b. So we can factor out dv. We can say that this is equal to dv to the power b times dc to the power b divided by n times dv minus 2 times dv dc to the power b. And now we factor out dv power b. So this is equal to dc power b divided by n minus 2 dc to the power b. So that's factoring out dv power b and then canceling dv power b. Okay, so now we finally have an upper bound that looks rather okayish. So let's put together what we have. So let's take a clean slate and say we have PCB is upper bounded by epsilon squared times dv choose b times dc power b divided by m minus 2 dv. Check. Yes. So here we made a mistake. This should be m minus 2 dv. Yeah, this is m minus 2 dv because we simplified these two terms away. So these two terms is what we simplified. Let me put this or write this down cleaner. Okay. So we have m minus 2 dv choose dv divided by n minus 2 dc power b times 1 minus 1 over dc to the power dv times 1 minus 2 over dc to the power 2b. Okay, so now we can put everything together. So now put everything together. So we need the sum from b going from 0 to dv of PCB. So now we factor out everything that doesn't depend on b. We can take in front of the summation. So that's epsilon squared times 1 minus 1 over dc to the power dv divided by m minus 2 dv choose dv times the sum from 0 to dv. Then we have dv choose b times dc. So now we multiply. So what we do is we write this guy as not 2b, but b, we write it twice. Power b times 1 minus 2 over dc power b. So we can take this dc power b and multiply it with this guy. So that gives us dc. Let me just put this on a numerator. That's going to be dc minus 2 to the power b divided by n minus 2 dc to the power b times 1 minus times 1 minus 2 over dc to the power b. So we don't like this guy, so we just say this guy is smaller or equal than 1, so that we can just get rid of it. And this, of course, is not an equality sign, but this is an upper bound, so that we can get rid of this guy. And we also want to get rid of, let's just get first rid of this guy. So this is smaller or equal than we just write it, epsilon squared times 1 minus 1 over dc divided by m minus 2 dv over, yeah, I'm going to do it in this way. So m minus 2 dv choose dv times the sum from b going from 0 to dv of dv choose b times dc minus 2 divided by n minus 2 dc to the power b. Now we can apply the binomial theorem. So this guy, so we know that binomial theorem, just the sum from L going from 0 to n of n choose L, x to the power L and y to the power n minus L is equal to x plus y to the power n. So we apply the binomial term to this sum and we extend this by 1 to the power dv minus b. Change it. And this is equal to epsilon squared times 1 minus 1 over dc to the power dv divided by m minus 2 dv choose dv times 1 plus dc minus 2 divided by n minus 2 dc power dv. So now we bound this further. So we say this guy is smaller or equal than 1. And this guy, now we make a rather unexpected change. So this is a small, it's not easy to see. So this is a small trick that we can do. So we can say this is smaller or equal than 1 plus 1 over 2 dv to the power dv. We can do this if n is larger or equal than 2 times dv plus 1 times dc minus 4 times dv. So if that holds, then we can say this is smaller or equal than this term. So this is just a rearrangement. So we can say that this guy is smaller or equal than this guy if this condition holds. It's just simple rearrangement of the two. This guy has a nice expression because this guy will converge to square root of e. So this guy, so 1 plus 1 over 2 dv to the power dv is smaller or equal than square root of e. And we don't like square root of e, so this is smaller or equal than 2. So we make a very, very crude approximation, but we're going to see it's sufficient because we just want something easy to express, and it's not going to be a dominant term, so we can make this crude approximation. So finally, we can put everything together. So we can say that finally, so the sum from b going from 0 to dv of pcb is smaller or equal than 2 epsilon squared divided by m minus 2 dv over dv. Okay, so now we have something that is rather simple, rather nice. And now we can summarize the two terms. So let's take a look at what we have right now to summarize. So to summarize, we have the following. We have the following. We have in the first case, case 1, we have the expectation of Bij times Vkl was smaller or equal than epsilon squared times P uij equals 1 times epsilon divided by m minus dv, choose dv. So that's the first case. The second case, we have the expectation of Vij times Vkl smaller or equal than epsilon squared times the probability that Uij is equal to 1 times 2 epsilon squared divided by m minus 2 dv, choose dv. And this is smaller or equal than epsilon squared times the probability that Uij is equal to 1 times 2 epsilon divided by m minus 2 dv, choose dv. So we just say epsilon is smaller than 1, so we can just bound this by 2 epsilon. Okay, so now we need to take the larger of the two terms. So which one is larger? And this is clear because here we have a factor of 2, and this guy will be smaller. This guy will be larger, this guy will be smaller, but it's in the denominator, so this term will be larger. So taking the larger of both upper bounds, we get the expectation of Vij times Vkl is smaller or equal than epsilon squared times the probability that Uij is equal to 1 times 2 epsilon divided by m minus 2 dv, choose dv. Okay, now we can put everything together. So now we have the expectation of n2ss squared equal epsilon squared times n choose 2 times p uij is equal to 1 plus, just going to write it again, sum over ij, sum over kl, such that ij is different from kl, the expectation of Vij times Vkl. Now we put our bound inside. So this is smaller or equal than epsilon squared times n choose 2 times the probability that Uij is equal to 1 times 1 plus 2 epsilon times n choose 2 times n choose 2 minus 1. Where do these come from? Well, these are just the number of summons that we have. The n choose 2 summons for I and j, and we have n choose 2 minus 1 summons for k and l. N choose 2 minus 1 because we don't count the ones that are equal, where ij is equal to kl. So and then we divide this by m minus 2 dv, choose dv. We multiply with epsilon I already was a little bit too fast. So we multiply with epsilon squared times p of uij is equal to 1. So now we can group and factor out some terms. We have this term over here. We have this term over here as well. So we can factor out this guy. So this is equal epsilon squared n choose 2, p uij equals 1 times 1 plus 2 epsilon n choose 2 minus 1 divided by m minus 2 dv choose dv. And that's it. So now we put everything together that we have. So we can now put everything together. So PE is larger or equal the expectation of N2SS. The whole thing is going to be squared divided by the expectation of N2SS squared. So if this is larger or equal, then the numerator is n choose 2 squared times epsilon power 4 times p of uij equals 1 squared divided by the bound that we have. So epsilon squared times n choose 2 times p uij equals 1 times 1 plus 2 epsilon times n choose 2 minus 1 divided by m minus 2 dv choose dv. Okay, time for cancelling. This guy cancels with this guy. Epsilon square cancels, and this guy cancels as well. So we have, this is equal to n choose 2 times epsilon squared times p uij equals 1 divided by 1 plus 2 epsilon times n choose 2 minus 1 divided by m minus 2 dv choose dv. So we don't like this n choose 2 minus 1. So we can say n choose 2 minus 1 is smaller or equal than n choose 2. That is then, because it's in the denominator, we can bound this. So this means that we can bound this. So it's larger or equal than n choose 2 times epsilon squared times p uij equals 1 divided by 1 plus 2 epsilon times n choose 2 divided by m minus 2 dv choose dv. Okay, so now we can further simplify this. So we can use the following approximation. So we know that this is equal to 1 over 1 plus tau. This is larger or equal than 1 minus tau, for tau larger than minus 1. This is 1 over 1 minus tau. This is larger or equal than 1 minus tau. So this is larger or equal than n choose 2 times epsilon squared times p uij equals 1. This is what we had before. And now we have a correction term, which is 1 minus 2 epsilon times n choose 2 divided by m minus 2 dv choose dv. So this is our correction term that we have. So now we could stop, but we will give further, we'll simplify it further in order to get rid of this possibly large binomial coefficient. So let's do this a little bit further. So say this is equal to epsilon squared n choose 2 times P of Uij equals 1 times 1 minus 2 epsilon. So n choose 2 is n times n minus 1 divided by 2, which allows us to cancel this 2 already, times m minus 2 dv, choose dv, is equal to m minus 2 dv times m minus 2 dv minus 1 up to m minus 3 dv. And on top, we have dv factorial. So now we can bound these terms. This one is smaller or equal than n. dv factorial is smaller or equal than dv power dv. Rather crude approximation. And the denominator here is larger or equal than m minus 3 dv power dv. So we put this together. Now we are almost done. So we can say that now PE is larger or equal than epsilon squared, n choose 2, times P of Uij equals 1, times 1 minus, say this, epsilon squared times n squared times dv power dv. So note that here we lower bounded, we upper bounded the expressions because we have a minus sign here. In order to get a lower bound, we need to upper bound these guys here because of the minus sign. So, and then we have m minus 3 dv. So let's just put this m is equal to n times dv over dc minus 3 dv to the power dv. And then by simplifying a little bit, putting things together, this is equal to epsilon squared, n choose 2, times P of Uij equals 1 times 1 minus epsilon. Sorry, this was not epsilon squared, this was an epsilon. Let me check if I made this correct before, times epsilon times n squared. Divided by n over dc minus 3 to the power dv. Okay. So again, you see that here we have the term that we had before, and then we have a correction term. This correction term scales as 1 over n to the power dv. So this correction term is the order of n to the power 2 minus dv. So if dv is large, n is small, this correction term. Okay, so we finally have everything together. So we can summarize what we have. So this is a theorem that we have that's proven. So we can state the following. So C is a regular dv/dc code with n larger than this term, which is rather not too bad, but this is a question that we have. And we use it for transmission over BC with the erasure probability epsilon. We also have DC to be larger or equal than 3. Could be larger or equal than 4, because otherwise we'll have issues of putting together the first case. So then the code word error probability after decoding is lower bounded by this expression, and this is further lower bounded by this approximation. And here we need to insert P of Uij equals 1, which is the probability that two randomly chosen variable nodes Vi and Vj form a size 2 stopping set, which we calculated in the previous video. So let's take a look at some examples. So here is an example. There's the code that we calculated before, and we show the lower bound. And we see that now it's a true lower bound, so slightly below, but it gives an approximation. So this curve is a fundamental. This is a bound. And we say that because of this bound, it means that the error probability cannot get below this bound. And this one is looking very, very bad. So it's decreasing very slowly. So the error probability cannot go above this bound. This is rather bad. So what we can look at next is also how this changes for various n. So we have a 3.6 LDPC code, and we look at the bound for various n. And we see that here we have the bounds. So even for n equals 5,000, we cannot get below a code word error rate of 10 to the power minus 5. So if we want to get a code word error rate below 10 to the power minus 5, it's not possible using this approach. So that's rather disappointing. So let's take a look at now a different code. So instead of 3.6, we can go to parameters 4 and 8. Well, now it looks significantly better. So with 4 and 8, with n equals 5,000, we can get in the order of 10 to the power minus 7 to 10 to the power minus 6. So we can hope for error rates that are below 10 to the power minus 6, but we cannot go below 10 to the power minus 7, even if we increase n to 5,000. So that's rather bad. So we need to do some tricks in order to get there. We're going to see later how to achieve this. Because if we want to achieve an error probability of 10 to the power minus 15, which we would like to have on a storage device, this is not where we'd like to be. So this is something that we significantly need to change. So with this, we're at the end of this rather long derivation. This derivation shows that if you want to get something rigorous, it takes a lot of effort. And if you want to get an approximation, this is significantly easier. But getting a rigorous lower bound is a significant effort, and it's not going to be easy to extend this to irregular codes and other codes as well. So with this, we're at the end, and now we're going to see how to get around this by eliminating some of those stopping sets.